Hello, Math 20-1 students. So today we're going to be looking at quadratic functions again. So in 3.1, parts 1 and 2, we looked at the quadratic function in vertex form. So we had a little bit of an introduction to what functions were. We talked about the vertex form of quadratic function. So now we're basically going to look at the same thing, but just in a different form of writing it, which is the standard form. And I think in the last video, I mentioned that I thought you might have learned that in Math 10, but I was forgetting that what you would have learned is just like the polynomial form of it and how to factor it, but you didn't actually learn the graphing kind of concepts with it. So that's what we're going to be looking at doing today. So let's see, there's a little investigation here, which is a reminder from last time, talking about when a football player kicks a football into the air and it reaches a maximum height before falling back to the ground. How can you mathematically model the path of a football through the air? So hopefully, based on what you learned in the last lesson, or lesson or two, I guess, you can kind of have an idea of how you can answer that. But because it is an investigation, I'm going to let you do that yourself. So if you want, you can pause the video and think of how that would work. And then we're going to move on to looking at this standard form. So basically we have a different form of writing this equation that you can see right here, which is f of x is equal to ax squared plus bx plus c, and this is the standard form we've been talking about. A standard form. Okay, so the path of the football through the air, like we just kind of mentioned there, is just one of many real-life phenomena that can be explained by a quadratic function, whether it's in vertex form or in standard form. Okay, so today we're going to focus on some real-life scenarios that are based around this standard form. Now, as we kind of started to look at last time, it's going to be important that you're able to use your graphing calculator for this. So keep in mind you do have to, if you haven't gotten one yet, it's very important that you get a graphing calculator in order to complete this course, because it's actually one of the curricular outcomes that you are able to use a graphing calculator. Okay, so you can't expect that you'll be able to do this by hand because we have to test you on your ability to use the calculator. Okay, so in this particular case, it says use your calculator to find the x and y intercepts and the vertex of the parabola. Okay, so we have this quadratic, which is y equals x squared minus 4x minus 12. So we're going to start out here by doing a little bit of an introduction of how to use your calculator. So like we mentioned last time, you're going to go into your y equals part of the calculator to actually enter in your graph. So if it's x squared, remember this is the button you use for x. I'm just going to bump that up a little bit in the screen here. So x squared. And then minus, so again, remember, I think I mentioned last time, but make sure that you're using the minus button, not the negative button for this one. So minus 4x minus 12. Okay, so now we have our equation entered into our calculator, and we can go to the graph. Oh, now I was doing a bit of a weird graph there last time, so you can see that my window settings are kind of weird. And so basically what I want to do to fix that is I can go to zoom. Now, if you want kind of a bit of a shortcut, you can always try doing zoom fit, which is where the graphing calculator will try to do the fit for you. In this case, I don't love the way that's turning out. So what I might do is go to my window and try to set my window settings to standard. Oh, whoops, sorry. Actually, you can do that in Zoom. I'm going to go to Zoom standard. So I'm going to go 6. Let's see how that looks. Okay, so now you can actually see from this that it looks pretty good. Like we can see quite a large range of the x values, but we can't see the vertex, which we definitely want to do. What do we need to do to see the vertex? Well, we would need to see lower down on the y scale, so more into the negatives. So this is where, once I have my kind of standard fit, I can go and do a little bit of tinkering by hitting window. And I'm going to change my y minimum. Instead of -10, I'm going to make it -20 and see if that's good enough. So now when we look, yes, we can see the vertex there. Okay, so that's good. So now that I can properly see this, I'm just going to move this down a little bit. So hopefully you guys can see the calculator a little more clearly. I know there's a bit of a glare coming in from the window. I might just pause this 1 second, see if I can fix that. Okay, I think that works better. I swear every time I start making a video, the sun comes out and just tries to mess with me. Okay, so now I can see the graph, and let's see, what were we being asked to do here? Use your calculator to find the x and y intercepts and the vertex. Okay, so we did y equals to graph the function. We did the window to adjust the parts of the graph that we could see. Now we want to start looking at answering these questions. So if we want to find the y-intercept, what we're going to do is hit second function trace. Well, actually, let me just see, because we could... Oh, I didn't put that in there. Okay, usually what I would do is... I mean, you could move it to 0. Let me just have a look here, because for some reason mine is not... Doesn't seem to want to move. Oh, there we go. You have to start out with down. Okay, so basically what you can do is, you might have to play around with it a little bit, but if you just hit trace, then you can move the arrow around until you can see it. And basically what you want to do is look on the bottom here, because it tells you where the cursor is on the graph. And so what you want to do is make sure that for the y-intercept, your cursor is where x equals 0. And we can see that when that happens, y is equal to -12. So now we can say the y-intercept is going to be x is 0, y is -12. Okay, so we can fill in that piece of information. Then we want to be able to do the x-intercepts. So in this case, we have to hit second function trace. Okay, so second trace, and then we have this menu of options, and it says choose 2, which is 0. Okay, so I'm going to hit 2. And you can either hit the number 2 or scroll down to it and hit enter. Either one will work. And then we want to find the x-intercept. So now what you need to do is you need to look on the bottom of the screen, because it gives you these little prompts. So it says left bound. And what that means is you want to be on the left side of the intercept you're trying to find. So let's say we want to start out with the x-intercept that's over here. We want to move this cursor until it's to the left. In this case, I mean, it kind of looks like it's above, but it's still to the left of the intercept. And it doesn't matter where, just any place to the left. Hit enter. It's going to make this little line. Although if you have an older version, it won't make the line, but still it's fine. And then it says right bound. So now you want to move your cursor to the right so that it's just past your intercept. Shouldn't matter exactly where, as long as it's to the right of it. Hit enter, and then it's going to say guess. And it's basically asking you, can it now guess what the x-intercept is that you're around? So you just hit enter again. And it tells us when x is -2, y equals 0. Okay, so that's one intercept. X-intercept is -2, 0. And then we have a second x-intercept over here on the right side. So we basically just need to redo it. So we want to hit number 2, and then we want to scroll over. Now left bound, technically I could have done it anywhere, but I just personally like to be a little bit close to the actual target that I'm getting. Right bound, so now I want to scroll over to the right side, and then it says guess. Remember to hit enter again. I don't know why, but students always seem to forget they have to hit enter that third time. So now it says when x is 6, y is 0. So I have my second intercept. Okay. And then the last thing is we wanted to find the vertex. So for the vertex, we are going to also do that second function trace. Okay, so second function trace, but this time we're looking for, now remember our graph is dipping down, so you always have to make sure you're choosing, is it a minimum or a maximum you're looking for? If the graph opens upwards, you're looking for the minimum. If it opens downwards, you're looking for the maximum. So in this case, we're going to choose number 3, which is the minimum. And then it's going to do the same thing. So left bound, so I want to scroll over. So I'm on the left side of the vertex. Hit enter. Right bound, scroll over. So you're on the right side. Hit enter. And then it's going to say guess. Hit enter one more time. And so here it says for the minimum, our x is basically at 2. Our y is at -16. So we can say 2 2, comma, negative 16 is our value for the vertex. Okay, so if you are not totally comfortable with that, then you might want to pause the video, try and go through those steps again on your own, because it's really important that you have these skills as we move forward. Okay, let's have a look at what's coming up next here. So we're going to do a little bit more work with graphs here. So we want to graph f of x is equal to negative x squared plus 4x plus 5. So, oops, I'm going to go into, y equals, there we go. And it's going to be negative. So again, remember when you're doing the negative, you want to hit this button down here at the very bottom, negative x squared plus 4x plus 5. Okay, so just to be clear, that was the function that was given there at the top. And now I can go to my graph. Now, right now my window is fine, so I actually don't really need to adjust that because I can see all the parts of the graph I need to know, which are the x-intercepts, the y-intercepts, and the vertex. Okay, so we're good with that. We don't need to move the window at all. Now the first question we have here is, does the graph have any symmetry? If so, explain the symmetry. So if you remember last time, we actually kind of talked about this, how the graph is a mirror image of itself on either side of a vertical line. And so keep in mind that means that we have a vertical line of symmetry. So does the graph have symmetry? Yes. It has a vertical line. Vertical line of symmetry. And that line is the one that goes through the vertex. So a vertical line of symmetry through the vertex. And that's why, if you remember, we talked a little bit about last time how it's very important to know the vertex, because it helps us to determine a lot of things, minimum, maximum, as well as where the line of symmetry is. Next one, is there a maximum y value or a minimum y value? Well, if our graph comes to a peak, which means it opens downwards, then we know that it's going to be a maximum y value, right? So we can say, yes, there is a maximum y value. And what is the values? This is where we need to be able to do our calculations. And so basically what we would need to do is go second function trace. Remember, in this case, we're looking for a maximum, so we want to choose number 4. Oops. Hit enter. And again, it's going to ask you left bound, so make sure you're on the left side of the peak. Go right bound, enter, and then guess, enter one more time. And so it says our maximum is at x equals 2 and y equals 9. So we can say there is a maximum y value of 9. Okay. Now last question, what is the x and y intercept? So x-intercepts we can calculate really quickly, and there's always going to be 2. So we want to go second function trace. We want to go to 0. And so we want to be, again, left bound. So here's one of our x-intercepts. We want to be on the left side of it. Then on the right side, hit enter for guess. And we find that x is -1 when y is 0. And for the other one, second function trace, choose 0. We're going to have, let's see, left bound. So here's our intercept. We want to stay to the left. Scroll over, hit enter one more time. And in this case, we find that, oh, why is it doing that? Every once in a while it'll do this. I don't know, it might be because I was doing too much stuff on it earlier. When you have a number like this that's like insanely small, like -1 to the power of -12, you can just count it as 0 basically. And actually when I did this earlier it did, so I don't know if I just need to redo it, if there was something funny with Yeah, see, this time it worked. So if you get a weird number like that where it has an exponent, you might just want to try redoing it just to confirm. So basically we can say 5, 0. I don't know why they do that sometimes. You never never know what's going on with this technology, right? Okay, and then for the y-intercept, so last time I kind of showed you, you can just do the trace. If you want. See, sometimes this is why I don't really like doing the trace one. So usually what I'll do if I'm trying to find the y-intercept is I hit second function trace. Oops, why did that not take me to, there we go, to the menu. And I just enter number 1, so the value. And that's going to take me to a place where I can just say, what is the x value that I want to know the y value for? So with the y-intercept, x is always going to be equal to 0. So I just enter the number 0, hit enter. And I can see when x is 0, y equals 5, which is my y-intercept. So I can write down 0, 5. Okay, so now we have most of the information that we usually need for a graph. So let's go into a little bit of an investigation. So using this same function, negative x squared plus 4x, right? So it's the same as the one we were working with, but in this case, we're going to count this 5 as a c variable, okay? And they want us to substitute in some different values for c to see how the graph changes. So if you feel comfortable, pause the video and go ahead and maybe try all 3 of these. If you need some help, then you can watch, but otherwise you can come back to this after you've tried it yourself. So basically what I'm going to do is I'm going to go into y equals, and I just want to change c, so I'm actually not going to erase this whole thing every time. So if I wanted to start out with, let's say 10 here, okay, so I'm going to hit enter, whoops, sorry, I'm not thinking not enter. I want to first put in number 10, so I just type it in over top of the 5 that was there, hit enter, go to my graph. Now you can see that I need to change my windows a little bit, so I might go zoom standard. Let's see if that works. Nope. Okay, so I can see that I'm going to need a higher value on my y-axis here. So I'm just going to go into window, my y maximum I'm going to make into 20. Okay, let's try that. Okay, so now I can see my graph. Now remember for the last one we had a y-intercept was at 5, and as we just saw we needed to change to 20 to even see the graph here, and our maximum value last time was 9. So let's have a look here. If we quickly do a trace for our y-intercept, we can hit value and then for x equals 0. Well, now we can see our y-intercept is 10, and last time it was at 5, right? So if we think about what we just changed, we substituted our c value for 10, right? So instead of the 5 that we had before, now we have 10, and we can see our y-intercept is now 10. Let's have a look at our maximum really quickly. Second function trace, maximum, left bound, right bound. And we have a maximum of 14, and last time we had a maximum of 9. So let's try one more here. So if we put in a value of 0, that actually means that we're just going to have nothing here, so we can just delete those out and go to our graph. And now we can see our graph is way further down, right? Before I had to make this window a lot larger. Now my my vertex is much lower, and my y-intercept I can see goes right through the origin, so 0, 0. So now instead of 0, 5 or 0, 10, I have 0, 0. And so you can probably guess what's changing is that the y-intercept is changing, so c is equal to the y-intercept. Okay, now you'll notice that in the filled in copy of the notes that I posted, I did write a little bit more in there, but that's just so that if you're not watching the video, you still kind of know what I was trying to say here. Next one here, using the function f of x f of ax squared plus 4x plus 5. So we see again the same ending to this, but in this case we're going to be changing the number that comes before this x. We want to substitute in some different values. So let's go back to this one. So remember we started out with negative x squared plus 4x plus 5. And let's maybe just have a quick look at what that graph looks like to remember. So this is our base graph that we are looking at. Okay, you can kind of see like we have a y-intercept of 5, a maximum of about 9, negative 1, and positive 5. Okay, so just remember that general shape. Now, if we want to substitute in negative 4 for this ax squared, let's go in. So in this case, unfortunately, I do have to, oh no, actually it's going to work. There we go. So negative 4x squared plus 4x plus 5. If we go to our graph, what looks different? Well, we can basically see that the graph, the vertex is a little bit higher in this one. The y-intercept is no longer at the origin, right? It's still higher up. So a little bit of a change there. Let's try a different value. Let's try negative 2. So I'm just going to change the 2, go to the graph. And same thing, so it still looks like it's at about the same position now, but it seems like the graph itself might be a little bit wider, you might have noticed. Let's try putting in a positive 1. Okay, so I got to get rid of that negative. And actually I don't even need any value there because it's just x squared. So let's go to our graph. So pretty big difference, right? And what is the big difference? Well, we went from negative values to positive values and the graph flipped. So this might be reminding you of some of the things that we looked at in the last section. So basically what we can say is the a value changes the direction of opening and the width. And so that is just like in vertex form. Remember that A did the same thing when we were looking at the vertex form. Okay, so that's kind of nice because if you're trying to remember how things work, at least you have one similarity between these two forms. Okay, next one we have, again, they want us to do the negative x squared. Negative x squared plus bx plus 5, right? So now we're going to be changing this value. Remember before we had the 4x, so just a quick reminder of what that graph looks like. There it is, okay? And they want us to substitute in some different values for b. So right now we have 4 in for our b value. Let's try putting in maybe negative 4. Let's see what that would be, the biggest change. So instead of plus 4, I'm going to put in minus 4. Go to the graph. And so what's the big change in the graph? Well, you probably noticed the graph seems to be shifted quite a bit over to the left, right? Let's try putting in positive 2 for the value. Y equals, or actually let's try 0. That should be good. Wait, no, that's not going to work. Times by 0. So then we would just go 0 times by x is 0. So it's actually just going to be negative x squared plus 5. Let's have a look at that graph. And then all of a sudden we see that it's centered with this axis of symmetry kind of right down to 0, right? So let's have a look here. I just want to try one more. So y equals negative x squared. Let's do plus 2x plus 5 was our other thing that we had in there. So it's kind of hard to see here. Let's have a look. Let's go in and trace and see what the maximum is, because in the last one it was right on 0. So we're left bound, right bound. the maximum was at y equals 6 and x equals 1. And we had put in a value of 2, I believe it was. Yeah, positive 2. So it's not actually making it our line of symmetry. So we can't say that this value here is our line of symmetry. But we can definitely see, like with positive 2, we see the graph is moved over to the right. With 0, it was centered across the y-axis. And then with negative 4, it was over here, right? So basically what we can see is that these b values are moving the graph left and right. So b moves graph left or right. And so let me just think about that. So 0 was further to the left. So basically as you go down, so lower numbers, or right. Oops. Jumping ahead in my writing. Okay, so it moves left if you have lower numbers, or right for higher numbers. Okay, so what are the conclusions we can make about these different values that we see in the standard form then? The effect of c on a quadratic function is that c is going to be exactly equal to what the y-intercept is, which is really nice because then we have an actual point on the graph. The effect of a on the function, and then do positive or negative values impact the function. So a affects shape. Negative a opens down. Positive a opens up. And bigger numbers make the graph narrower, right? Bigger numbers equal narrower. And again, I have this written out more nicely in the filled out notes that I posted, but that's so that you can read them without me explaining them. Okay, what effect does the changing of value b have on the graph of the function? Moves graph left or right, right? We just kind of went over that. Left or right. Okay, so now we have a little bit of an understanding of how these different values are going to impact whatever graph it is that we're obtaining from this. Okay, so there's a little bit of a summary here of everything that we just talked about. And let's give an example a try. So for each quadratic function, identify the following. So the direction of the opening is the first thing. So in this one, obviously the direction opens up. Okay, and if we look at that, we can see, remember we said that a determines the shape, and there's no a value here, but x is positive, so remember that means that basically we have positive 1 as our a value, and because it's a positive value, it's expected that this graph will open up, so that's good. Coordinates of the vertex, what do we have there? Well, we can see that the coordinates are x value of -3, y value of -4, -3, -4, okay, which we don't really see reflected in this equation directly, right? So just we can kind of be aware of that. The maximum or the minimum value, well, in this case, because it opens upwards, we're going to have a minimum. And the minimum value is going to be y is equal to -4. Let's see, what is the equation of the axis of symmetry? Sorry guys, my headphones just died there, so hopefully this will keep on working here. Okay, so axis of symmetry, right? So going up along here, we can see that our x-axis is going to be, or sorry, not x-axis, axis of symmetry is going to be x equals -3. The next thing we needed to do was x and y intercepts. So for our x-intercepts, we are going to have -5, 0, And we're also going to have a second one, which is going to be -1, 0. And then for our y-intercepts, we are going to have up here. Now this one's a little bit trickier because it's kind of hard to see up here, but remember what we just learned, which is that our y-intercept is actually given directly in our equation. So if we weren't sure if this was a 4 or a 5 or a 4.5, we can see right here that it is 5. So our y-intercept is going to be where x is equal to 0 and y is equal to 5. Okay. Last thing, domain and range. So with the domain, remember, we're going to do those squiggly brackets, and again we can say x is equal to all real numbers, which you guys are undoubtedly familiar with now, and then range is going to be our y values. So remember, with the range, because we have a minimum for this one, we would say y has to be greater than or equal to -4, and other than that, y can be equal to all real numbers. So then we can do that little symbol again as well. Okay, let's look at this next graph. We have to do the same things. Which direction is it opening? Well, in this case, it's opening down. What are the coordinates of the vertex? So it's going to be at +1 on the x-axis, +4 on the y. Okay. What is the maximum or minimum value for this one? Because it opens downwards, we have a maximum value of y being equal to +4, like we just saw. What else do we have? Maximum or minimum axis of symmetry. So that's going to be our other value from our vertex. So x is equal to +1. Number 5, we want to do x-intercept is... We're going to have 2 of those. So the first one over here is -1 and 0. And then our second one is going to be +3 and 0. Our y-intercept, we can look on the graph, or we can look here and we can see that it's going to be +3 for the y and 0 for the x, of course. So those are going to be our coordinates. Now the last thing is domain and range, and I'm actually going to show you guys a little something different for this one. So we've, like up until now, we've just looked at doing the, the squiggly brackets, but there is actually another way that you can record domain. So normally we've been saying x equals all real numbers like that, which is fine, but you can also put it as brackets and as like a set of coordinates essentially, so with the maximum and minimum of the x values. Now, because x can be all real numbers, the maximum and the minimum, the maximum is +infinity and the minimum is -infinity. So whenever you have an infinite value as your domain or range, you use circular brackets, like semicircular. So we would say, okay, so on the lower end, we're going to be looking at -infinity. On the upper end, we're going to be looking at +infinity. So this is a different way to write domain. Okay, we can do the same thing with range. So normally for range, we would have written y has to be less than or equal to 4, and y could be equal to all real numbers. Ooh, that was a bad bracket. Okay, or in this new way of writing it that I'm showing you, the lower value is going to be infinity. So we're going to use a circular bracket to start out with. And so it can go anywhere down into -infinity. But the other value is that it has a maximum. So it has to be at the upper range, it has to be 4. And so when we have a specific number value here, then the bracket that's next to it has to be square like that. Okay, so if we would have had a specific number like here where we had a minimum, then we would have written it as square bracket -4, comma, +infinity, circle bracket. Okay, so it's kind of weird and there's like kind of stuff to remember with it, so that's why I haven't really introduced it, but you should just be aware that if you see this, that it is a legitimate way to write domain and range. But pretty much for me, I'm always going to stick with writing it this way because I just feel like it's less stuff to kind of try and remember. And I will accept either way of writing it that you guys choose to do it if you're writing on a test. Okay, so I just want to make sure. Oh yeah, we've got just a couple more questions. So here's where we're going to actually look at analyzing these as if when we're using real life situations. So we can start to see how these quadratic functions apply to real life. So in this one we have Vanessa jumping from a 3-meter springboard with an initial velocity of 6.8 meters per second. Her height in meters above the water t seconds after leaving the diving board can be modeled by the function height, right? So her height is a function of time, which makes sense, right? However much time is passing is how she's going to kind of be moving through the air. And so then we have a bunch of numbers here, negative 4.9 times by t squared plus 6.8 times by t plus 3. So they're asking us to first of all sketch the function. So we want to first graph it on our calculator and then just do a rough sketch of it. So I'm going to go into y equals, and it's going to be negative 4.9x squared plus 6.8x plus 3. Okay, so that's our graph. And it says to use the window negative 10, 10, 1, negative 10, 10, 1, which is our standard window. So we can go into that zoom and choose Z standard 6. And now we'll be able to see the graph as it gets built. There we go. So here is our graph, and we want to do a quick sketch of the function. Now, if you are being asked to sketch a function, the things you want to be aware of is that you want to include a proper, somewhat proper kind of like estimate of it in terms of your values, right? So I would kind of make a couple of points here. I'm going to have an x-intercept just kind of to the left, a y-intercept not too much above that, vertex up here, and then looks like kind of like that is what I'm going to be looking at. So then I'm just going to sketch through there. Ooh, that might not be as good as I wanted it to be. So when I actually drew it, I'm also terrible at drawing these kinds of things. I'd probably say that that looks a little bit better, even though now it looks like a bit of a nightmare there, but whatever. But the really important thing now would be that if you're going to sketch it, you need to give some of the points. And so we kind of want to look up what are some of the different points here. So our maximum, remember we can go second function trace, find the maximum, left bound, enter, right bound, enter, guess. So our maximum here is where x is equal to 0.694, let's say, we'll round that off, and y is equal to 5.359, let's say. Okay, the other thing we want to look at is our x-intercepts. So, and by the way, so this right here might show you why you might want to use a pencil, and then you can erase it and kind of redo it a little bit better. And when I did it, like for the printed copy that I posted online, I did that. So I just kind of did it outline first really lightly and then colored it in. Okay, so let's go second function trace. We want to find zeros. So left bound, right bound. Oh, and it's doing that thing again. Let's try that again. 0, left bound. Maybe just make sure you're a little bit further away so that it really knows what you're talking about. So here we can see that we have x is equal to 1.74, let's say, when y is equal to 0. And we can try our y-intercept as well. So second function trace, value, x equals 0, enter that. And so we can see here, when x is equal to 0, y is equal to 3. Now, you could think, okay, well, should we look for this other point on the graph, which is the other x-intercept. Why would I maybe not need to look at that? So think about what we're actually graphing here. This girl is on a springboard that's at a certain height, 3 meters above the water. Okay, so if you think about this graph here, try and think about how would it visually relate to what you see when somebody jumps off of a diving board. Well, here we can see on the y-axis she's at 0, or sorry, on the x-axis she's at 0, on the y-axis she's at 3. And what do we see as a familiarity? Well, she's on 3 meters high on the springboard, right? And we said in our function h of t, which is basically the same as y, right? It's kind of like f of x, but in this case we change the variables to match what is actually in our equation. So this one we're worried about height, and time is our x variable. But these are basically represented on our y-axis. And so this 3 meters height is in meters, which is our y variable. So it's showing that she starts at 3, right? She's going to jump up, hit a certain point, and then go back down as she moves towards the water, right? So would this x-intercept here have any relationship to basically what we're trying to figure out? Not really, right? Like if she's starting her jump from here, this is kind of like a unimportant piece of information, so we can kind of ignore that. What about this other x-intercept? Well, if you think about how someone jumps, they jump up, they go down, right at the point where we're at 0, right? So if the diving board is 3 meters high, what's at 0 meters? Well, hopefully the water, otherwise she's jumping in the wrong direction. Right, and so that's also important because it can show us different information about how she's moving towards the water. So what does the y-intercept represent? It's basically the height of the springboard. Height of springboard. Okay. What maximum height does the diver reach? So remember at the vertex we had 2 different values. The y value is our height, so we can say max height is 5.359, and they told us that the units are meters. When does she reach that height? Well, her time, the variable t, is in seconds, and we found that the t value on the x-axis was 0.694. So 0.694 seconds is when she hit that maximum height. How long does it take before the diver hits the water? Well, she jumped from here, went up, went back down, so we want to think, how did she move in time, which is basically our x-axis, right? And then our y-axis is height. Well, our x value when she's at 0, which is the water, is 1.74. So it took 1.74 seconds for her to hit the water. Now again, please notice that the ones I filled out online are much more like what I would expect for you guys to fill in for a test, which means full sentence answers, right? But just when we're doing these recordings, I don't want to make you wait while I write everything out. So please refer to the posted filled in notes to make sure that you understand how I would expect an answer to properly be filled out on a test. What domain and range are appropriate in this situation? So we kind of had a question like this last time. Remember when they're asking appropriate for the situation, you do actually want to think about, you know, the actual physical situation that's happening. So in this case, for domain, we're looking at our x values. Would it make sense to start at a negative time value? Well, obviously not. And so basically we need x to be greater than 0. And in this case, because she finishes the dive or hits the water at 1.74 seconds, we don't really need to think about anything past there. So now we have a new way of writing domain, which is basically that x has to be greater than or equal to 0. So you always are going to put your value in the middle, and less than or equal to the 1.74, which is the end of the dive, if you don't count what's going on below water. Okay, same thing for range. What do you think is going to be appropriate as a range? Well, let me just think here. Where do they start at? So they start at 3 meters high, but they finish at 0 meters, right? So that's going to be our minimum, even though it's on the other side. So don't get confused because they don't happen in the right order. So y has to be greater than or equal to 0. And less than or equal to, so she started at 3, but remember our y value still goes higher than that because she jumps up to start out with. So it has to be less than or equal to that maximum height, which was 5.359. Okay, so there's our appropriate range. What is the height of the diver 0.6 seconds after leaving the board? So for this, you can go into your calculator, and we want to determine a specific value, 0.6 seconds. Remember that that means t value, which we said is on the x-axis. And so all we need to do is go second function trace. We want to put in a value for x, which was 0.6. Okay, so just type that in, hit enter, and now it shows when x equals 0.6, y equals 5.316. So her height at that point was 5.316, 316 meters. Okay. All right, so we have one more question to look at here really quickly. Writing a quadratic function to model another situation. So Farmer Boswell wants to build a rectangular pig pen using 96 meters of fencing. And we need to write a quadratic function in the standard form to represent the area of the pig pen. So in this case, basically, we want to think about what is the formula for area of a rectangular shape. Well, it's always going to be area is equal to length times by width. Okay, so we need to think about if you're going to build up, you know, this rectangular kind of shape thing, what could be the length and what could be the width. Okay, so so we have this rectangular shape and we have 96 meters of fencing, right? So we know for sure that we're going to have to divide that 96 up. So one way to do this would be to think of if you can put on, let's see, what would 96 divided by 2 is going to be 48. So if we were to say, okay, each one of these sides here is 48, then we still need to figure out what these sides would be. So if we've divided this evenly, but we need a certain value here, x, right? There has to be some kind of a width there. So then that means that if the width here is x, this length has to be equal to 48 minus x, and this one also has to be 48 minus x, right? So that you have the relationship between the different sides shown there. And this isn't the only way that you can do it. You can come up with other ways as well. You could have done 96 divided by 4, which would have been 24. Although then you would have just had even kind of numbers all the way around, so then it wouldn't have really changed, set you up for a function. Yeah, I don't know. I'd kind of have to work through that and see if that would work out. But for now, let's stick with this one. So we've divided the distance up evenly between these two, and then we're going to have some variable value here because we're trying to figure out what would be the best dimensions to maximize the area using this much fencing. Okay, so we have 48 minus x, and then we have x as our unknown. So if we want to fill this in, let's say that this is our length side and this is our width side. Then basically what we can do is we can fill in these algebraic expressions for this. So area now becomes equal to length, which was 48 minus x, times by width, which is just x. Okay, and then of course if I want to simplify that, I need to multiply out the brackets. So remember that when you do that, you have to multiply everything. So 48 times x is 48x, and negative x times x is minus x squared. Okay, so here we have a equals 48x minus x squared. Now the only thing is write it in standard form. So remember that standard form starts out with the x squared value, then the x value, and then any single number values. We don't have a single number value, so there's basically no c value, which it inadvertently tells us that it's 0. But if we want to write this out in the proper form, we have to just switch these two around so that the x squared is first. So the negative has to stay together with our x squared, so negative x squared. And then this is positive 48x, so we're going to do plus 48x. Okay, so just always remember to keep your negatives together with the thing that comes right after it, even if you move them around in the equation. So there's our standard form of this. Now it's asking us to sketch the graph, so let's go in and actually plot it out. So we have negative x squared plus 48x, and let's go into our graph. Now here you can see that this graph is not even close to fitting on here. So I'm going to go to zoom, and I'm going to see if I can do zoom fit, so I can get a little bit of a better idea. Okay, so we can see that now we're seeing quite a bit more of it, but we're going to need way more, right? So right now we're at 1, 2, 3, 4, 5, 6. Oh, sorry, standard window, I think is what this would be. So it's going to be at like 10. Let's go into our window. Oh, no, it's actually way more. Okay, so our y scale is really big, but our x, we need to have way more going over to the right. So let's make our maximum 30 and see where that gets us. Ooh. Okay, it's still not nearly enough. So we need way higher on the y now. I don't know why it looked like we had enough on the last one, I guess because it didn't go up far enough. Let's do y max, I don't know, 500. And let's do x max 60. See where that gets us. Okay, so almost good. We just need a little bit higher on the y. So let's go back into there and let's do y maximum, maybe 600. Yes, okay, so we have it all fit in there, perfect. And so again, I'm not like, I'll just do a really quick kind of sketch here so we can see that it goes through the intercept here. I really hate making you guys watch me do this because when I do this on my own, it's like kind of painful. I'm definitely a math science person and not an artist. Okay, so now I have kind of my main important points, and if I can go in, I'm going to check for my different intercepts. I'm not going to walk you guys through it again because I kind of showed you that and I don't want to make this video too long. But if you do your traces, you'll find that we have 0, 0 here. When you check your maximum, you're going to find that you have 24 and 576 as your maximum. And then when we get back down to this axis, we're going to have 48 and 0. Okay, so go in and do your proper traces though, just for practice, and check and make sure that you get the same numbers, and then you know you're doing this right. Now, one important thing to kind of keep in mind, just like we did in the previous one, is which axis is what, right? So here, if we look at our format, A is basically equal to Y. So this is showing us our area on the Y-axis. And on the X-axis, what are we basically seeing? Well, X, we said, is the width. So this is kind of like our width measurement. Okay, so it says, what are the coordinates of the vertex? Well, we said 24 and 576. And what does that represent in this situation? Well, think about what 24 is. 24 is on the x-axis, right? That's our 24. And it's giving us our width. So basically, 24 is our width. And the units were in meters, right? Because we had 96 meters of fencing. And so what's on the y-axis here, going across like this, is 576. And that is our area. And what is that going to be if it's at our vertex? That's going to be our maximum area. which is going to be 576. And then again, thinking about units, and this would be important on a test, because we had meters of fencing, area is always a squared unit, right? So the maximum area that he can build for a pig pen with that amount of fencing is 576 meters squared. Okay. Determine the domain and range for the situation. So again, we need to make sure that this is appropriate. And so with this one, it's a little bit tricky because we do have, intercepts at 0. But does it make logical sense to have, so if we think about like specifically here, both x and y are 0, does it make sense to have a width of 0 or an area of 0? No, right? And so when we're talking about domain, which is our possible x values, we basically would say that our x has to be greater than 0. Okay, now we're not going to say specifically what value it has to be, and it has to be less than 48, right? So we can't have a width that's more than 48. Okay, so basically what we've done to adapt this to the situation is we're not putting equal to, because even though we can see it get almost down to 0, you need to have more than that. Realistically, of course, for like having a big pen, you have to have it be for sure more than 0 as one of your dimensions, quite a bit more, but we don't want to really like speculate on that in this kind of a question. So we're just going to give the basics. So in terms of range, our y values, again, we don't want to have it equal to 0, so it has to be greater than 0, and it has to be less than our maximum area, which was 576. Okay, so that's our maximum. Identify any assumptions you made in modeling this situation. So if you think about what we were told we had 96 meters of fencing, and when we were figuring this out, what did we assume about those 96 meters? Well, we basically assumed that you would try to use every single last little bit of that, right? We didn't say like, take 4 off or 6 off for waste or whatever like that. We assumed that you would be able to use all of it for building this pig pen. So we assumed all material was used. Okay, so that is graphing quadratic functions using the standard form. So hopefully that was helpful for you. You have some work to do based on what we learned today. And let's see, next time we will be looking at, what are we looking at next time? Oh, completing the square. And I'm pretty sure that, now I shouldn't probably say this, but I'm pretty sure you guys did something kind of like this in Math 10C, but it's been quite a few years since I taught that course, so maybe I should stop guessing. So I will see you in that lesson.